chemists, I'm going to be clarifying and expanding on a few things that I've already covered about acids and bases and how they react with each other, and then a little bit of work on how we're going to be using that in this topic, ending with a new K value. Not the last one, there's more. Okay, so when we are talking about acids and bases, we're talking about things that have an excess of hydronium ions, that is an acid, it's got a lot of H+, or an excess of hydroxide ions, that's a base, and that's OH-. In water, water has a pH of 0. That doesn't mean there's 0 hydroxide or hydronium. It means there's very little, and it's the same amount of each. So that's just when water's just chilling, relaxing, doing whatever, it by itself disassociates into a little bit of hydronium and a little bit of hydroxide. At 25 degrees C, which is room temperature, that number is very, very small. There is 1 times 10 to the negative 7th moles per liter of hydroxide or hydronium. Very, very small amount, but not 0. This number here is one that we will be using later. You don't need to remember it, but you'll see it again. When you put an acid into water, you're making basically you are adding hydronium ions to that water because they come from the acid, and that means the solution is more acidic. Ditto for bases, we're making there be more hydroxide. So acid is a measure of how much excess hydronium we have, and base is a measure of how much excess hydroxide we have. When an acid and base react, you form something called a salt. A salt is just another word for an ionic solid. Salts, however, are not always neutral. So when you have an acid and base react, you're not always going to get a neutral solution. That could be because your acid was much stronger than your base, meaning that when they've totally reacted, you've got still some acid left over. Or it could be because the thing that they make when they react is itself an acid or a base. To use this example here, this is ethanoate. This is ethanoic acid. When you have ethanoic acid, you produce ethanoate, which is itself a base, and that accepts hydrogen ions to make an acid, and that makes the solution, to make a base, and the solution itself is then alkaline because you've used up those hydroxide or the hydrogen ions from the water, leaving only hydroxide left, meaning you end up with a base. Those are kind of edge cases. You may see them from time to time, but really the main thing to remember is that when you have an acid and a base reacting with each other, the stuff you end up with is not always going to be neutral, and you can calculate what the pH is actually going to be based on what goes on. Okay, on into pH. pH is a measure, like we said, of the amount of hydroxide ions, and it is equal to the negative log of the concentration of hydroxide, of hydronium, H3O. That's what we say here. Negative log of hydronium is the same thing as pH. P stands for power or potential of hydrogen, not percent. People sometimes say percent. It's not percent. It's power or potential. It can be calculated with this equation right here. pH equals negative log of H3O, negative log of the concentration of H3O, rather. You can rearrange that to go the other direction. So if you know the pH, but you don't know the concentration of hydronium, you can calculate it by doing 10 to the negative pH. So you can go from one to the other. pH equals negative log H3O. H3O equals 10 to the negative pH. You can go back and forth. And pH values. If pH is equal to 7, that is saying that the concentration of hydroxide here and the concentration of hydronium here are equal to each other, and that number is equal to 1 times 10 to the negative 7th. Told you you'd see that number again. That means that the pH is 7. That's the definition of pH 7, is a solution where this is true. If your pH is less than 7, you have an acidic solution because you've got more hydronium than hydroxide, and also you've got more hydronium than the normal amount, which is this amount here. And if pH is greater than 7, it's the same thing, except you've got more hydroxide than hydronium, and more hydroxide than the normal amount. It means that pH is greater than 7. Okay, pH and pOH are related to each other. pH is the power of hydrogen, POH is the power of hydroxide. pH plus POH always sum to be 14. So pH plus POH always equals 14. So if you know pH, you also know POH. And POH works exactly the same as pH, except you're dealing with concentration of hydroxide instead of hydronium. So POH equals negative log of concentration of hydroxide, and you can rearrange so that concentration of hydroxide equals 10 to the negative POH. Basically, you can convert from one to the other easily, and once you convert from pH to POH easily, rather, and then once you have POH or pH, you can find the concentration of hydroxide or hydronium, and the other way around. Okay, so now into our new K number. There is an equilibrium constant for weak acids. Why weak acids specifically? Because if you have a strong acid, you don't need a dissociation constant. You don't need a constant to work it out because the concentration of hydroxide for a strong acid is the same as the concentration of that acid. Because every single HCl dissociates into H and Cl, you have exactly as many H's as you had HCl's to begin with. So you don't need to do anything fancy to work it out. When you have a weak acid, it does not fully dissociate, and therefore you need a way to work out how weak it is, how much it dissociates. And that is why we have a Ka. So Ka is only for weak acids. If you have a really, 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 really large Ka, that's another way of saying this acid is strong, it fully dissociates. So we're going to be dealing with Kas that are not very big, because if it's very big, then it's strong. Okay, Ka is calculated from experimental values, same as Kc, same as Ks. Ka is a number that that is basically, they do experiments to work out what it is. And it tells you how much the acid will dissociate, basically how weak is the acid. Strong acids fully dissociate, weak acids don't fully dissociate. Ka is how we find out how much they do dissociate, and therefore how strong or how weak is the acid. So in water, weak acids dissociate to form H plus and H3O. Strong acids do too, but we're dealing with weak acids. And they also form a conjugate base. So we've got an acid, HA. It's called HA because A for acid, H because there's a hydrogen. If there wasn't, it wouldn't be an acid. And its conjugate base, A minus, is A minus because it used to be an acid, but it's missing a hydrogen, so it's got a charge of -1. So HA is always going to be the acid, A minus is the conjugate base. Okay. And when they're in water, they dissociate. So HA plus water is in equilibrium with its conjugate base, A minus, and hydronium, because the hydrogen left the acid and went over here to the hydronium. Okay. So this dissociation can be written like this. K sub C, not K sub C in a minute, but K sub C for now, is equal to concentration of the conjugate base times the concentration of hydronium, that's the products here, over the concentration of the acid. Why don't we include water? Because you never include water. Can't have a concentration of water. Water is what things have a concentration in, so water just gets left out. So it's calculated the same way we do anything else. Concentration of products times each other times the concentration of the reactant. When we're talking about acids specifically, we use something called Ka, and it's just a way of saying this is a Kc, but it's for an acid, so it's Ka. And you write it like this. This is just what we saw on the previous page. Again, that's it. I'm going to assign some work associated with this. Sorry this video went long. When you only got one a week, this is what you deal with. Thank you guys very much. I'll talk to you next.